In this video, we'll first consider the temperature and density in different parts of the Sun, then look at the conditions that have to be met for fusion to occur, and then look at the multi-step fusion process in the Sun. As part of this study, we're going to learn about some unusual particles and processes that exist in the Sun. This slide is a review of some things we've looked at before. Something has to produce a lot of power. The Sun's power output, you can see there, 3.86 times 10 to the 26th watts. That's enormous. If you prefer not to use scientific notation, you can read it in standard notation. And the Sun's been doing this for a long time. The oldest solar rocks, those we find in asteroids, are more than 4.5 billion years old, closer to 4.6 billion years. And only nuclear reactions can produce that much power for that long. Chemical reactions and gravitational contraction just don't do it. So let's take a look at something. This will be a conceptual exercise that we can kind of understand. That red rectangle there is supposed to represent a slab of solar material somewhere in the Sun. And things like that don't just fall down to the center of the Sun, even though the gravitational force acting on them is in that direction, and they don't get pushed upwards. They're more or less in equilibrium. The forces on them balance. The force from above is produced from gases that are above the slab. The weight of the slab is also pulling down on the slab, but there are pressures or forces from the gases that are below the slab. The forces are balanced, so the two downward forces have to be balanced by that upward force. And that means you could continue this process going lower and lower into the Sun, but what you'd end up with is that the pressure has to increase as you drop down closer and closer to the center of the Sun. This isn't all that unusual. Something like this happens in the Earth's atmosphere. The pressure increases as you go toward the surface of the Earth. But what happens is that the pressure at the center has to be enough to support the weight of everything that's above it. On the surface of the Earth, the pressure is 14.7 pounds per square inch. If you took a 1 square inch piece or column of air from the surface all the way to the top of the atmosphere, it would weigh 14.7 pounds. So that's the case in the Sun too, except the Sun's a whole lot bigger, so the pressure at the center is going to be much higher. Well, how do you make a gas pressure or a plasma pressure higher? You do it by increasing the temperature and increasing the density of the plasma. And the next slide we'll look at that. The top graph shows how the temperature of the Sun increases as we go from the surface, which is 1.0 on the horizontal axis, to the center. The temperature at the Sun's center is about 16 million Kelvin. That's hot. We can determine this by looking at the total energy outflow of the Sun and matching that to what we know about the energy produced in fusion reactions. The bottom graph looks at the density of the solar plasma. The units are different than what we've looked at before for density. Here they're kilograms per cubic meter instead of grams per cubic centimeter. In these units, the density of water is 1,000 kilograms per cubic meter. So you can see that at the center of the Sun, the density is about 160 times that of water. In the next slide, we'll see why both the high temperature and the high density are required for fusion to occur at a sustained rate. Nuclear fusion is the joining together of small nuclei. Don't confuse that with nuclear fission, which is the splitting of large nuclei like uranium or plutonium. Nuclear fission is what drives the nuclear reactors in power plants, large Navy ships, and submarines. It's also what produces the explosion in an atomic bomb. Fusion is something we hope will someday power electric generation plants, but we have yet to get our technology to that point. It's very difficult. The process in the sun takes part in a few steps that we'll look at in detail. The Coulomb barrier isn't something that is at some point in space. Instead, it refers to the repulsion between positively charged nuclei, which has to be overcome if they're to get close enough together for the strong nuclear force to latch on and hold them together. In order for nuclei to overcome the Coulomb barrier, they have to be moving very fast, which they do at high temperatures, and they have to be moving in pretty much a head-on path. Any slight side-to-side deflection and they're just going to veer off and miss each other. To have a reasonable chance of a head-on collision with another nucleus, they have to be in a space densely crowded with other nuclei, and summing this all up, they have to be in a region of high temperature and high density. So let's look at step one of nuclear fusion in the sun. We start with two hydrogen nuclei coming together and fusing. A hydrogen 1 nucleus is just a proton, so we have two protons coming together and fusing. But instead of forming a nucleus with two protons, some odd process takes place where one of the protons turns into a neutron. It turns out it's a bit more fundamental than that. It turns out protons and neutrons are not truly elementary particles. They're actually made of something more elementary called a quark, and just one of the quarks in a proton will change into a different type, and that's what changes a proton into a neutron. And it's the weak nuclear force that's going on there. I mentioned that there was another force at work, and we're not going to look at the details of that. It's complicated. But then there are other things that come out besides that hydrogen 2 nucleus, which has a neutron and a proton in it. So the E plus on the right side of that thing is a positron, which is short for positive electron. It's the antiparticle of an electron. They were first discovered in 1932 after having been predicted by theory earlier than that. And they're now commonly used in a medical diagnostic technique called positron emission tomography, or a PET scan. And you can have one of those done in Moses Lake. There's actually a truck that hauls a trailer over from Wenatchee a few times a month, and you can have that diagnostic technique done here. There's one more particle to show up here. That other weird symbol is the Greek letter nu, and that's the symbol for a neutrino. Neutrinos are things that were proposed by theory in about 1930. It wasn't until the 1950s that they were first detected. The instrument that was used to detect them was built down at the Hanford Reservation, the site down there. Neutrino is a word that means little neutral one, as opposed to a neutron, which is a big neutral one. But anyway, the neutrinos are little things. For a long time they were thought to be massless, but it turns out that they have a very small mass. The next smaller particle that we know of is the electron. That's the smallest one. It's about 1/1750th the mass of a neutron or proton, but an electron is more than 4 million times the mass of a neutrino. So electrons are tiny, neutrinos are even tinier. They're electrical neutral, so they aren't affected by electric charges or electric fields. They're also immune to the strong force. They fly right through ordinary matter as if it wasn't there, and only occasionally interact with something. A huge number of neutrinos go through you every second, and you just don't feel them. Maybe once in your lifetime, one of them might react with something in your body, and that's most likely going to be a dead skin cell on the surface of your body. Here's a picture of that first step in the process. The orange balls are protons. They've got a plus sign in the middle of them. The blue ball that's the same size represents a neutron. And the picture also shows what happens to the positron. it meets up with an electron. That's an E with a little minus sign on it. And the two annihilate each other, and two gamma ray photons are produced. Let's take a look at step 2. In this step, the hydrogen 2 nucleus from step 1 is smacked into by another proton, and a helium 3 nucleus forms. Energy is released in this fusion, carried away by a gamma ray photon. And here's the cartoon version of step 2. You can see the hydrogen 2 nucleus with a neutron and a proton smacks into another proton, and this time nothing weird happens. You just have a gamma ray photon carrying energy away. And the wiggly red arrow is supposed to represent the gamma ray photon. On to step 3. This one occurs when two helium-3 nuclei that had been produced by step 2 somewhere within the core of the sun combine, and they form a helium-4 nucleus, which actually, if you add together all the parts that are there, you'll end up short a couple of protons in the helium-4 nucleus, and those two protons are released in this reaction. It's not quite as interesting as the first two steps. We don't have any weird little things coming out or gamma ray photons, but those protons move away at high speed, which means they have a lot of kinetic energy. And here's the picture version of that step. Now, a few facts about the nuclear fusion. A key point about mass: the net reaction turns 4 protons into a helium nucleus with 2 positrons and 2 neutrinos flying out, as well as gamma ray photons. Now, the total mass before this process, the mass of 4 protons, is 4.029106 U, and a U is a symbol for an atomic mass unit. After the process, the total mass of all the particles, the positrons, the helium-4 nucleus, that's basically what you have that you didn't have before, is less than that. It's 4.002054. So there's an extra 0 after the 4 before you get to the first non-zero digit. And actually, 0.67% of the mass has disappeared. Where did it go? What happened to that? Well, here's the hint. E equals mc squared. That missing mass has turned into energy. It's the energy of the gamma ray photons, the kinetic energy of those protons that came flying out in step 3, and you end up with 26.7 million electron volts of energy every time one of those helium nuclei is produced. A typical chemical reaction, on the other hand, produces energy in the order of just plain electron volts. This is 1,000,000 times that much, and that's something that's very powerful about nuclear fusion. So what happens to the stray parts? Those stray parts are positrons, gamma rays, and neutrinos. Well, the positrons almost instantly meet up with electrons. They annihilate each other, and in that annihilation, they produce 2 more gamma rays. The positron and the electron are gone. That's what annihilation means. Poof, they're gone, and 2 photons come flying out of that little mini explosion, and that's it. But they're very high energy photons, gamma rays. And then those gamma rays are slowly radiated outward, and they're absorbed and re-emitted many times. Remember that material at the center of the sun is very dense, okay? And it absorbs light, and the gamma rays will get absorbed by an electron or a proton, something that's flying around, and then re-emitted, but they're typically re-emitted with less energy than they had when they came in, the re-emitted photon. There's kind of a downhill progression where the photons released after having been absorbed have less and less energy. Eventually, by the time they percolate out to the surface of the sun, they're in the visible part of the spectrum. The energy generated at the core takes 170,000 years to reach the surface of the sun, and then only 8 minutes to reach the Earth, because once it leaves the sun, it's traveling through the vacuum of space at the speed of light. This isn't terribly unusual. There was actually a technique in early passive solar energy houses where someone would build a solid masonry wall, like solid concrete or something like that, on the south side of a house and expose that to sunlight all day. After being exposed all day, it would take the warmth until evening to start showing up on the inside of that wall. Then it would sort of percolate into the house through the night when there was no sunlight falling on it. That was something that was only about a foot thick. And you think about how huge the sun is and the crazy density at the center of it, it would take light from the center a long time to get through that material. Well, we haven't talked about the neutrinos yet. What happens to them? Well, again, they're neutral, so they're not affected by electric charge. They're not affected by the strong nuclear force. They're barely affected by gravity because they're going at nearly the speed of light and they have very little mass. And the only force that acts on them is the weak nuclear force, which has a range about 1,000th that of the strong nuclear force. So the neutrinos fly out of the sun through all the sun's layers at the speed of light and head out in every direction from that. They just go flying out. So this is the tail end of the nuclear fusion in the sun process. So we'll have a couple of videos that look at other things as well.